Okay, 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 okay. Oh, I think we've had a little technological glitch. Technological glitch. Oh my gosh, bit of a technological glitch there. I don't know what was going on. Right, right. What we doing? What we doing? What we doing? What we doing? Yeah, fractional distillation. You guys, this came up in 2018 actually. Fractional distillation. Um, do you guys know what temperature fractional distillation happens at? So I'm just going to talk about fractional distillation very, very, very quickly because obviously chances of it coming up are slim. But you got to know the temp that you do fractional distillation at. Came up 2018. It's based on the intermolecular forces, size of the molecules. You know all that crap. So that's all right. Do you know the difference? Do you know the conditions for thermolytic cracking and for catalytic cracking, or thermal cracking and catalytic cracking? Make sure you know the difference between those. Um, Hopefully, you guys know that. 350 degrees, well done for fractional distillation. Yeah, zeolite, slight pressure, bigness. See, that's for the catalytic cracking. Obviously, zeolite's a catalyst. Absolutely. Um, do you know which one of the two, catalytic or thermal cracking, gives you the aromatics? What one produces more aromatics, and which one produces the alkenes? Yeah, catalytic is aromatics. Nice, 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 nice. All right, good, 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 good. Just moving on, of course, of course. Now, what the hell is this image? Well, you guys have to know, obviously, um, when we burn alkanes, when we burn hydrocarbons and combust them, um, we can produce sulfur dioxide, which causes acid rain. What are they using? This is called a scrubber. They spray this on factories on the end of the flue. Do you know what substance this is to get rid of the sulfur dioxide? Calcium carbonate. Absolutely. Yes, yes, yes. Calcium carbonate or CaO. Nice, nice, nice. I know, I know. I ain't hanging long on this stuff. Just if it comes up. It's come up before. Come up 2018. It's come up before. So, ozone. Just make sure you know your ozone stuff. I know it's basic. Just make sure you know your two ozone stuff. Make sure you know um, why CFCs were used. So, why were they used? CFCs, non flammable, non toxic. So, really good, unreactive, non flammable, non toxic. However, they damage the ozone layer and they replace them with HFCs. HFCs do not contain chlorine, so don't form the chlorine free radicals that break down the ozone layer. Anyway, coolio, coolio. Let's look at haloalkanes. Just thought I'd remind you of that stuff. And if there's anything in your brain that's going, oh, sugar, I need to look at that before tonight. So, haloalkanes, make sure, are you all cool with nucleophilic substitution of haloalkanes by hydroxide ions? So, just to remind you very, very quickly, won't take long at all. Just to remind you, you guys are all cool with this, right? Yeah, easy peasy pudding and pie. But just quick reminder, yes, 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 yes. Okay, so then you can do the nucleophilic substitution. What about, let me give you this one. Okay, folks, someone tell me the product here. Oh, Sugar Ray Leonard, what is that? It's my board, that's what it is. All right, hold on, folks. Hold up, hold up, hold up, hold up, hold up, hold up, hold up. I'm gonna go bonkers. Stonker bonkers. All right, guys. What product will I get if I use sodium hydroxide in anhydrous, which means there's no water present, ethanolic conditions. So if I'm going to go with aqueous ethanolic, basically anhydrous without water, so you can ensure that by having just alcohol. What product am I going to get here, peeps? Not propanol, not propanol, not propanol, not propanol. No, 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 no. Eh. Big Nissy's on the right track. Propene, thank you. Alkene, yeah, propene, propene, propene. So just remember, if it is AQ, if it's AQ, you're going to get the nucleophilic substitution. You're going to get that thing happening. But if it is, come on, pen, don't let me down. Okay, what type? Yeah, I should have given you butene. Then I could have tested you on. Do you know where the double bond forms? Let me give you butene, and then you can tell me where the double, what the name is gonna be. Oh shit! Come on, oh, man. Sometimes this stuff can be a pain in the ass. Excuse my language. I'm tired, so a bit loose. Um, where are we? All right, flip back, dude. Oh no, no, not rubber. Don't give me rubber. Don't give me the rubber. I don't want that stuff. All right, guys. What is the name if I use ethanol? There we go. And bromobutane. Bromobutane and ethanol. Can you tell me the product? Which product? Which product? Butanine. What are the two possible products? Two possible products. Two possibles. Yeah. So you're absolutely right. Yeah, of course, we can have OH minus. Remember, the hydroxide ions are going to attack. Oh my good God, good Lord. The hydroxide ions are going to attack here, and then that is going to like put your double bond there, right? So we can have a double bond there, and then that is going to dislodge. So it's always the carbon adjacent to the carbon with the halogen on. You're going to get the double bond. And of course, that is going to affect what you can have dependent. That's going to affect your options dependent on where the bromine is. So just remember, if the bromine is over here, this gives us options for the elimination. So this is only if it's ethanolic, anhydrous, ethanolic, whatever. We can have this, and then, oh shit, that's not going to get me a mark, is it? I'm showing, excuse my lord, excuse my language. Right, that's going to go there. So I could get butanine there from that, but no, no, no. What am I doing? Oh my gosh, I'm falling apart. Yeah, we could get that there, or we could get that going there. So we got some when the bromine's here, you could get butanine or butanine. So just check when the bromine's in the second position, you can get butanine or butanine. So anyway, enough of that on the haloalkanes. Let's get off of haloalkanes. Let's go. What is that? Oh, that's just addition polymers. You guys are good with addition polymers. Teflon has the formula. You guys will be fine with that. Yeah, it's just Teflon, that's the monomer for Teflon. And Teflon forms, yeah, addition polymer, easy peasy. All right, let's look at the practical. So you've got a practical. You can either hydrate cyclohexene to make cyclohexanol, or the more common thing is they're going to react hexanol with phosphoric or sulfuric acid concentrated, and that will dehydrate us back to an alkene. Okay, so depending on the conditions, you can either turn cyclohexene to cyclohexanol, or we can go from cyclohexanol. Basically, you can go from alkene to alcohol or alcohol to alkene. The more common one is them to go alcohol to alkene. So let's do cyclohexanol to cyclohexene. How are we going to do that? What conditions do we need? Yeah, and then how will we purify it? So yeah, see if you can do that. I just got to deal with something. Give me 1 second. Got to deal with my coffee. Teflon is just it's just ethene with no hydrogens but just fluorines, and then you imagine if you do an addition polymer, it's just going to be all C's with F's all around it, and the ends of the brackets open, so it's easy. I will go to exam questions. Yeah. You guys are right. You guys are right. We got yeah, check the slurp. That's the coffee. Keep me going. So you can use a sulfuric acid or a phosphoric acid catalyst, concentrated of either one will do. Heat under reflux. Absolutely. You're gonna heat under reflux. No. No. Boom, 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 boom. Right, yeah. Okay, so we heat under reflux. Now we've got the majority of our product. We've probably got some excess hexanol, whatever. We've got some leftover unreacted cyclohexanol and cyclohexene. So how do we purify it then, guys? How do we purify it? 83 degrees. So Petrovich, I don't know, we've got some idiot in the chat. Hold on, let me deal with it, idiot, and then we'll get on and do some questions. I'll put some questions up, guys. Might be easier to go through some exam questions. You know, you get some addicts, right? This time of night, there's some real... Oh, what's going on with my mouse? My mouse has had it. My mouse is caught on something. Yeah, you got some real weirdos in the chat. You just have to watch out for these weird dudes. They turn up every now and again. So let's get rid of that dude. Get the beep out of here. You have been destroyed. What you have is you have some people that are a bit like loserish. So what do you call it? Uh, what are we gonna do? What are we gonna do? Let's put him timeout. Hopefully, I put the right person in timeout. Otherwise, oh yeah, we put him in timeout because he's a bit of a dweeb. You know what I mean? All right, let me give you some questions. Let's just do some. Let's do some exam questions. You're right. You're right. Let's do exam questions. You know you're right. What do you want to do? Arrhenius equation. How will you look with the old Arrhenius can come up? Let me have a flick through. Let's go. Let's have a flick. We don't want multiple choice. Uh, oh, there's an Arrhenius. I know you guys love a bit of Arrhenius equation, the Arrhenius equation. I can't stand it myself, but there we go. Right, what is this? We've got a rate. Okay, let's do this one quickly. Rate. So, by the way, reaction rates and Arrhenius can come up. So we'll have a quick. Let's go through this topic. We'll go for a couple of Arrhenius questions, a couple of ones working out reaction rates, orders of reaction, etc., and then we can move on to the organics. All right. So you'll need a calculator. I don't know, really, a kind of random organic chemistry questions, whatever you guys want to go over, really, whatever ones you want to go through. I'm just going to do questions. Just going to do questions. I was going to go through and talk a whole load and crap, but I'm too tired, man. You can see my red cheeks. I'm actually burning up. I think I'm getting ill, man. I've been doing too many lives lately. Um, yes, Yasmin Ahmad 304. Big shout out to you. Yes, this does come in paper two. Don't worry, you can smash this nice and easy, right? So look, if they ask you for this, calculate a value for the rate constant at this temperature and give its units 3 marks. So we need to get the rate constant K. So what we're going to do, we're just going to swing C and D underneath here like so. And they've given us the rate. So what was the rate of reaction? The rate was 3.1 times 10 to the minus 3. We want to smash that over 0.48. So this is a really nice, easy one. There's no point in giving you a difficult one and destroying you straight away. So, and then all we got to do is calculate that. So who's got an answer? Anyone got an answer? Oh, gosh. Boom! 2727 with the 0.028. I think yeah, 0.027, whatever it is. Yeah, let's round it, 0.028. So you come to the bit that some people find hard. This is the units. So look, what we're going to do, the units for that, they're giving you that in the concentration. Anyone got the units? Who's got the units? Mol dm minus 3 s to the minus 1. That is always the units of rate. So when you're doing the rate constant, you just write down how many of these you've got. So this is how I do it. Mol dm minus 3, mol dm minus 3. You can add these all up. So you'd have mol to the 2 dm minus 6, right? That would be mol to the 2 dm minus 6. But I ain't bothered with that because we're going to cancel those out. And that's going to, oh my God, what did I do there? That's just disgusting. I don't know what I did there. Let's get rid of that. That was foul. All right. Let's cancel that out. So you can add those together, but then you're going to cancel anyway. So you're going to end up with s to the minus 1 mol dm minus 3 divided by s to the minus 1, or the other way around, s to the minus 1 divided by that, and then that's going to reverse that, so you're going to get mol to the minus 1, because you're dividing with a minus 1 there, and then you're going to get dm to the 3, and then s to the minus 1. And there we go. Oh my days. Oh, who's trolling me? Oh, no, yeah, I'm going to ignore it. I'm going to ignore it because, like, yeah. I ain't got that kind of time, to be honest with you. I'm not sure, Fardo. I think they like you to write to the minus 1 rather than a dash. Yeah, I don't think they like the dash, but I ain't 100% sure on that. All right, we've got the arse-holiest equation over here. So link K equals minus EA over RT plus LNA. We could just do one of these and then we'll do one from the graph. These can be quite disgusting. Let's put... so hopefully everyone's all right with that. Let me try and make that a little big for you, man. If Petrovic was here, he'd be getting excited about this because it's getting bigger and anything like that makes him happy. So... an equation and that relates the rate equation K to the activation energy EA and the temperature T is this. They're giving us an arrangement of the Arrhenius equation. It doesn't always come with the natural log K, natural log A, but you can do that. Use this equation and your answer da 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 da. So we need to rearrange this. What are we actually finding? What do they actually want? I can't even see the question. Oh, we need to calculate a value for EA in kilojoules per mole. By the way, this is going to be in joules, so we're going to need to divide by 1,000 when we get this. So when you have the Arrhenius equation, normally you're going to work out the activation energy in kilojoules per mole. Also, you see it's got a dirty minus in front of it. This is just a word of advice, an exam technique. Activation energy is going to be endothermic. So if you end up with a negative answer, just get rid of the negative. It's like when you do combustion equations, when you're doing calorimetry. Doesn't matter what your symbol is that you end up with. Calorimetry is always exothermic, right? Sorry, combustion is always exothermic because you're burning a fuel. Right here, activation energy is the minimum energy to break bonds, and we know that bond breaking is endothermic. So let's smash this in and see what you guys can get. Obviously, you're going to rearrange that to make EA the subject. There's more than one way to do this. So you could start by minusing the natural log of A, or you could add EA to each side, and you could end up with, and then you could minus L natural log of K or whatever. So you could end up with like this. No, there's different ways to rearrange it. It doesn't really matter. Oh, come on, Tom, you utter buck. If it's going to be the positive way, then we're going to go. If we're going to do it with the EA as positive, then you're going to have ln A minus ln K, and of course times RT. What does that equal? So if we do that, that's going to give us the activation energy, and you're just rearranging that to make EA the subject. I know you can do it where you get minus EA is equal to natural log K. I could keep calling it ln, but natural log of K minus natural log of A times RT. Okay, is everyone cool with that? And then this is 4 marks. Why is it 4 marks? Because we need to work it bloody out, that's why. So I'm going to go 16.9 minus, what is K? K is 0.028 over here, guys. So I'm going to do minus 0.028. Oh, we need to natural log that. So let me natural log minus 0. Where's my log? log 0.028. All right, 3.578. So what I get here is 3.578. So if you natural log k, you're going to get minus 3.578. Oh, come on, Tom, sort it out. Minus 3.57, something like that. 16.9. What does that equal? And then we want to times RT. R is 8.31. And then surely temperatures in Kelvin is going to be 298, right? 25 plus 273. Anyone got an answer yet? Because I'm so slow on this one. Yeah, I'll go. I don't mind going over NMR. We can do an NMR after this. 50.7. Yeah, well done, well done, well done. Multiply by 1,000 or divide. You're going to divide by 1,000. So you should have got about 50,000. I don't know what that is. What's that going to equal? Let's do it. Right. 16.9 minus 3.57. So I don't know. I got 20.47. It might be 20.48. Don't. I think it's like about 20.48. That's probably supposed to be an 8. I probably should have rounded that to 5.8. Whatever, 20.48, something like that. And then times whatever the hell, 8.3. What is 8.31 times 298? Yeah, 2,476. I got something like that. So that was like, this is for RT, 2,476. I'm just trying to break it down for you guys with my blind ass. And then let's times by 20.48, and that is going to give us, I got 50,716, something along them lines, right? So yeah, so I got like 50,716. What the fudge? Yeah, I put an extra naught in. What a twit. There we go. I got that. 50,716. Bear in mind that's going to be joules. They ask us here for, sorry, that is not in kilojoules. That's joules per Kelvin. That's why we know this is in joules, because 8.31 is in joules per Kelvin. So we know that's joules. But the question, where are you, activation, asks us for kilojoules. So we're going to divide by 1,000. We are going to get like 50.7. And lovely jubilee. We're going to get like 50.7 after we divide by 1,000. Great, you guys got that. Let me find one with, give me a second, peeps. I just want to find one with a graph for you, for those of you that love a bit of EA. All right, let me give you the Arrhenius graph, and then at least we can tick off Arrhenius, and we don't have to look at this again. And hopefully after tomorrow, you'll never have to look at the Arrhenius equation ever again, unless you're doing chemistry at A level, at uni, and then yeah, enjoy it. So, yeah. Let's go. Um, oh my God. Okay, we're doing Arrhenius at the moment. I'm not going to be able to follow the chat until after I've finished the topic. So once we've finished this Arrhenius question, then I'll have a look. And once this question is done, if you put up the topic you want to go on, we'll go over a question on that topic. Probably we should go over like orders, if you're cool with finding out the orders of reaction when you're given the different concentrations or the initial rates. Now what you're going to do with this, you need to do the change in y over x. So it's really nice and simple. All you're going to do here is over here for 3 marks, calculate activation energy. Exactly the same. We're using the Arrhenius equation again. Look, it's got all the elements. Natural log of K, 1 over T. Now, there is a rule that you need to know. The gradient in an Arrhenius graph, and that is a natural log of K plotted against that, you need to know this off by heart, is equal to minus EA over R. So essentially, temperature has been taken out. So essentially, if I want to find the activation energy, all I'm going to do is the gradient of that line there times 8.31. And this will always be what you got to do. And that is going to give you the activation energy. So the gradient times 8.31, boom, 3 marks. So it's actually really easy. What I would say is, watch out for these numbers here. Sometimes these disgusting numbers are like 1 times 10 to the, they'll give you the log up there. So they'll put this as like 1.2, 1.3, 1.4, and then they'll say 10 to the minus 3 up here, like 1 over T, 10 to the minus 3. They'll do something crazy like that. So just make sure you check the units and you're sure what the units are. And then it is just a case of going like that. OMG. Look at that disgusting line. Thank ye. Right, so bussing a line across there. Look, I'm doing the whole thing. You don't have to do the whole thing. You can just do a little section, but I'm like, why would I do that? I'm going to make it easy as I can for me. Easy peasy pudding and pie. We're going to go like that. And then for the gradient, we just want to do the change in y divided by the change in x. That gives me the gradient times by 8.31. Lovely, but jobly. Right, we might have to divide by 1,000. We'll have a little look. Oh yeah, we will have to, because remember, this is in joules per Kelvin. So that's in joules. So we're going to get our answer in joules. So if they want it in kJ, we will have to divide by 1,000. So always check that out against R. So I don't know what this is. This, I'm going to say this is 0.00128 because it looks like it's 2 cubes there and da-da-da-da-da. That's, yeah, it looks like it's 2 cubes, little baby cubes before there. So I'm going to say that, and then that is bang smack on there. So 0.018. Now, it might be different to the mark scheme, but that doesn't matter. So I'm going to go 0.0018 minus, you can smash this in the calc and see if you can handle it. Can you handle it? And then you're going to divide that by the change in x over here, which is, oh my good lord, what is that, minus 3.8? No, that's minus 3, so that's minus 2.8. I hope that's minus 2.8. Is that minus 2.8? That's minus 2. That'd be minus 3. Minus 2.8, that looks like. And then that is minus 14. So I want to go, whatever. I'm looking at the difference, right? So actually, I don't even want to stick the minus in there. What's the point? I'm looking at that. We don't want minuses and minuses make a plus. Hold on. I think I've done that wrong. Is that line... Is that minus 2.6 or 2.8? I can't even see. Do you know what? My eyesight ain't good enough, peeps. I'm going to be honest with you. The eyes is not that good. Okay. Oh my god. Why did I put minus 14.8 there? Look at that. Look at this dipstick. Alright, let's go with that. Let's go with that. So, let's go with that. Anyone got an answer? Anyone got an answer? Anyone got an answer? You can do to the left. It don't really matter, but, you know. What does it matter, huh? I don't think it's going to matter. Whatever. Okay, so just to simplify for you guys. Hold on a minute. You utter dipstick. That is what I am. I'm a proper dipstick. Look, that is X. That is Y. Hold on a minute. So don't do that. You want to do 0.00052. That should be underneath because that is X and that is Y. Let me just correct that for you there. Those of you that spotted that, well done, well done. If you spotted that, so that's what happens when you're tired. As long as you spot it before you shot it or whatever. What is that? 11.2. Oh my gosh, I should just stick it in the calculator. It's that time. It's that time when I've actually got to stick it in the old calc. There we go. So that is change in. Oh my Lord of mercy. Change in y over change in x. There we go. So x. This is y. Horizontal is x. Come on, people. X axis, y axis. I didn't even spot that right. So 11.2 divided by 0.00052 equals. Give it to me. We got 21538. Does that sound right? I don't know if that sounds right, people. 0.46. And then I guess I'll divide by 1,000, right? You don't have to remove the minus, but activation energy is never going to be. I just don't like the minus. You know, you can rearrange and times into the minus and the minus and the minus and the minus. Oh, why did I remove the minus on XY when I was doing minus 14 minus 2.8? Because if you're doing like you're looking at the difference and then you're going to end up adding them together. So I just want what's the difference between 2.8 and minus 14? Yeah, actually, what's the difference in cubes on the graph, in squares, in units, not like a mathematical calculation there. So yeah. Anyway, yes, lovely. Put your answer there. Lovely jubbly. What is that? That's going to be 21.6, something like that. I don't know. 21.5, sorry. Hope that's right. Might not be. Oh my gosh. That don't look right. Hold on. That don't look right. Let's redo peeps. I've flopped on something there. Oh my god, I can hear my crazy kid screaming next door. No, activation energy is not negative. Hold on. Before my brain falls apart, the change in y, minus 14 and minus 2.8. Let's just make sure I've got that right. 11.2. And then, what did I make out the change in that was? Oh, fudge. Honestly, it's so late. My brain is not working, folks. I didn't even try. I didn't times by 1.8. What a utter freak! Look, this is why I'm so tired right now. So, what did I say that was? 21. I forgot to times by. Look, I haven't times by 8.31. What a spaz. Okay, so let's do this again. 0.0018. Take away 0.00128. That gives me 11 point. That gives me 0.0052. I want to do 11.2 divided by answer equals. Smack that out there. I get 21,538. You know what it is? It's tiring work, man. I did a 4 hour yesterday, so honestly, I woke up this morning and I had tuition and I was like sponked. Times 8.31 equals that 1789, basically 179,000 I got. So and then I'm gonna divide by 1,000, so 179. I got roughly that, and so the answer is going to be roughly 179. They'll give you a range because everybody's this is going to be slightly different. Obviously I forgot to do that, so there we go. Right, let's move on. What topics? uh I'm not sure if it will come. NMR, rate determining step. NMR, please. NMR. Rate determining step. NMR. Um, can't ban me, weirdo, bald PRC. Oh my god, some people just get so excited, don't they? What are we going to do? So, what? Um, All right. Let's have a little. We'll have a look at some. Let me find some amines or some rate determining step or something to do. So, yes, yes, yes. Don't forget to hit the like, folks.
If you push the button,
Like me.
Would you like it?
Like.
Okay. Let me find you guys something. All right, all right, all right, all right, all right. Yeah, yeah, yeah. Fair enough, fair enough. Cheese Louise. All right, we've done enough Arrhenius. Let's not do no more Arrhenius. Let me give you some mechanisms and see if you guys are on it with the mechanisms. I'm scanning through some papers, peeps. Give me 2 seconds. Let me give you guys a question while I scan read for your topics. Okay. Let me give you guys a question. All right, have a go at this one. I'm just going to scan read for your topics. This is a nice little rate one for you. It's got a rate determining step there that someone said in the comments. Am I muted? No. Okay, I'm not muted now. So see if you can work out the missing ones here. It's 3 marks. Calculate the missing values, and then have a go at that. And then what I'm going to do is I'm going to have a little look. Somebody said amines, so I'll slap up some amines if I can find it, or NMR, whichever one comes first. So give me 2 shakes of a cat's tail, people, while I have a little look through a paper and find you an NMR or an amine. What's that? That's polymerization. What's that? Amino acids. Amino acids. Data book. I don't want a data book. What's that? That's lab. Practical. Got the practical on. If you want to have a go at a practical on hexene and hexanol, which we were looking at, hopefully you know all of that. I can go through that with you. Hopefully you know how to draw the reflux diagram and draw the distillation diagram and where to put the condenser and where the water goes in and out. So let me know if you want me to show you that, and then we can go through an NMR if you like. Do you guys want to go through an NMR? Hey, anyone good at this? 1, 0.16 and 1.3. Yeah, we go through NMR. Let me smash through. Let's go through this first then. Oh my gosh, is everyone cool with working this out? Is this all bread and butter for you guys? What's happened? My drawing tools have gone. Why is that not working? What's happened? Have I frozen or something? Hold on. Hello. What is going on? Oh no, there we go. There we go. I'm back. All right, so what we got to do in experiment 1, they increased it by 25%. They kept this the same, that the same. Yeah, but we've got to know what the oh, they're giving us the rate equation here. That's all right then. So A is not even in the rate equation, so that's just going to be 1. Does everyone get why that's 1? Does anyone need that explaining why that is still 1? Does anyone need to know what a rate is 1? Anyone need to know why that is 1? Okay, MPT 0311. The reason why this is still 1.00 is because anything that doesn't appear in the rate equation has no effect on the rate. So the fact that they've increased that by 25%, it does not increase the rate by 25%. It has no effect on the rate, because the two factors, the two things that are in the rate equation, and by the way, that has a little 2 next to it, so that means this is second order and this is first order. So that has an exponential effect, and that just has a linear effect, and this has no effect. So the rate, as these two have been kept the same, equals 1. Now here, what we have done is we've kept that the same. What has happened to the rate here? Let's have a look what's happened to the rate. OMG. The rate has gone down. By how much has the rate gone down? And then you should be able to work out by how much this has gone down. They've kept this the same, so and this doesn't affect the rate. That has no effect on rate. So we should be able to work out what the answer is there. And this, so what we got 1. It's gone down by 0.64. Now, as that's the exponential, that means that if I square root 0.64, so we want to square root 0.64, what do you get if you square root 0.64? No, not square root. We want to go 0.16. Oh my good gosh! Hold on 1 second, folks. Aha, 0.16. You were right in the chat. What the fudge has gone on here for this last one? So 0.16. That doesn't count. Okay, so if we compare it to this has gone up by 50%. Oh my days, that's disgusting. I mean, we could just calculate the values by licking them in there. So yeah, you don't have to do it like this. We can just calculate the values by slapping them in there. Yeah, you're right. It's going to be 1.35. I'm just doing it the long way. You don't need to do it like this. You can just substitute the values in there. I'm such an idiot. You know, it's late. I'm tired. Right. Hopefully you guys all know that the rate determining step must feature stuff that is in the rate equation. Both the things must feature in the rate determining step. So in the amounts, they must feature in the rate equation. So we've got B here. Plus H plus goes to that. So that's not the rate determining step. Which step is the rate determining step? It's going to be step 2. Yes, it is. It's step 2. And the reason why we know it's step 2, because look, the B is to the power of 2, and it appears like that in the rate equation. And then we got the H plus ions in the correct thingamabob. So the reason is, yeah, you kind of like B to the power of 2. Yeah, you've got them in the right amounts. What should I really put? Will the examiner give me the marks for writing that? Probably not. I need to say both the reactants that are in the rate equation occur in the rate determining step in the correct amounts according to their orders. Right. Oh my gosh. What we want to do is do some NMR. People are asking for NMR. My gosh. Watch me flop on the NMR. Okay, hold on. I've got some NMR somewhere. Here we go. And that has got that lined up. So let me just put that there. And then what I want to do is... Let's put that there. Hold on. What I need to do is copy and paste. Bit of a copy and paste job here. Come on, mate. Sort it out, mate. Oh, later. Alright, it's coming, folks. Hold up. We're coming on. We're going. No. I've got so much crap open. Close that. Come on. Don't fail me now. Alright, and then we're going to piece this together. So it's a little 6-mark NMR. I know you guys love the NMR. You love it. I'll talk you through it. Hopefully I won't flop, but you know, I can't guarantee maximal integrity. Okay, here we go. There we go. Alright. Here we go, folks. Ooh. Right, what I need to do is go over here and I need to just get that up on screen for you guys. What the fudge? Yes. There we go. Woo! Oh, let me get rid of my face. Let's go down here. Come on, see. He's got his hat on. Oh, man. Okay. Oh, shit. Sugar Ray Leonard. Okay, so NMR. What's KZ? Alright, just so you don't have to hear me slurping coffee. Okay, so quick smart. Let me go through this for you guys. You want to give yourself about 6 minutes if you're doing NMR. Check the time. Give yourself 6 minutes. Do you need to get the complete... Some people said, oh, you can skip NMR and get an A star. I'm not sure about that. I don't think you can in A-level chemistry. You can't skip NMR and get an A star. What they probably mean is you don't have to get the final structure right. In AQA, you can get 5 out of 6 by following a method and getting 5 out of 6 without getting the structure right. So in OCR, you're only going to get about 4 out of 6 for that. The question is about X with the empirical formula. Look, the empirical formula is C2H4O. Lovely bubbly. So what we're going to do, sometimes you'll have to work that out. Nice, easy mark. They'll give you the percentage and then you've got to work out the empirical. It shows the infrared spectrum of X, the CNMR spectrum of X. The spectrum of X shows 4 peaks with different chemical shift values. This is just one. There's hundreds of these. What I would do is I'd look at this. Now, if you look in your data table, this is going to be, you should learn this one off by heart. It is the most common infrared peak, right? It's the most common one in exams. That is bang on 1700. If you go to your data book, 1700, who knows what 1700 is? So you're going to go IR 1700 equals the COO bond. It's actually between like 1720 and 1750. So I should probably put 1750. Look, if we want to check it, we can slap up here and we can go here and have a look here. And if we go to the infrared, you can see over here, it's about 1680 to 1750. If you want to write the range, you can write the range. It's up to you what you want to do. So we're going to come back down here and that you're going to start picking up marks by doing this. Where the hell am I? I'm over here. Okay. So much rubbish written on this PowerPoint over here, which I haven't cleaned up. So IR is 1700 COO. You've then got, look, we've got another IR peak I'm interested in. That's about 3,400. What do you reckon that is? That's probably, I don't know. You can get an A star skipping NMR, but why skip it when, look, we're picking up marks here. Look, we're picking up the marks on the IR here right away. Why bother skipping it? Like skipping the questions, you mean, or just the NMR bit? What do you mean? Because I wouldn't want to skip it. Like if you're going to play, why skip it? It's actually really easy to get the marks. It's hard to piece it together. It's easy to get the 5 out of 6. So don't skips. Right. Now we're going to look at 3,500. Look around here. It's either going to be amine or alcohol. How can it be amine? We had C2H4O. So it's not amine, right? It's going to be over here. We have, yeah, it was over 3,300. It's going to be the OH for an alcohol. So we're going to come back and we're going to acknowledge the OH for an alcohol. I think there may have been another peak. I don't want to keep flicking around these flicking back and forth, to be honest. That's one of the annoying things when you do these online, is the constant flicking back and forth. So flick, there's one at 3,000. So this is, I'm just going to write 2 here, yeah, and then I'll have a look at the other one after, because that may actually be important. So IR 3,000, what's that, 3,000, I don't know what, 3,300 to 3,500. And we're going to say that is giving us the OH bond, not for the carboxylic acid. The carboxylic acid, I think, is around 3,000, 2,600 to like 3,000. Let's go back and double check because of that. And I'm going to come back in a sec. Where's the carboxylic acid? Carboxylic acid is 2,500 to 3,000. That just looks like it's a CH bond, that other one. Yeah, the other one just looks like a carbon-hydrogen bond, so that's fine. I'm not going to get too excited about that. I don't think it's going to be, we're going to have an alcohol and a carboxylic acid. I think that's going to be doing too much, but we may have. We will see. We will see. Now let's come down to the CNMR. So far, we're going to have picked up some marks by commenting on the infrared. So maybe we picked up 1 mark, maybe we picked up 2 marks, but it's definitely not worth skipping. Now we come down to the CNMR. So we know they've already told us there are 4 peaks. So I don't think we're going to get, for saying there's 4 different carbon environments. Maybe I want to do that. This is this, is that this, what the, huh? Yeah, this is the CNMR. So this is going to tell us there are 4 carbon environments. OMG. And then, I don't know what that is. There's one at 20, one at, oh God, what is that? That's like 20, 28. That is, I'm just trying to, 72, and that's like 210. So what you might want to do is go back and say, these are my ppms, and this is what I believe those environments might be. And so you're commenting on the CNMR, and you're hoping that that's going to get you some marks. So we go to the CNMR over here, and we comment on, we're going to get to all the splitting patterns and that. I've totally forgotten what those numbers were, but we don't have a nitrogen atom, so it's not this. It looks like it's the conformation of the carbonyl group, right? We had a couple at 20. We had a whole bunch here which are just CC bonds, right? We had a whole bunch there. They're just going to be CC bonds. It looks like we got confirmation of this. This was like around 50, and then I think there was one around maybe 50 to 90, which might be the ester, which you could put that in as well. There was one around, yeah, 50 to 90. That is going to be alcohol or ester, CO. So I would just put those in. I just want to make a couple of comments on CNMR. That's one I did on another day, so don't watch that. So that's one, because this is one I use from my live on NMR. This is just a blank that I've just copy and pasted in. So what the arse was I saying? Right, so we might want to say CNMR, and we might want to say, like, I don't know, the one here at 72 is like CO of alcohol. And we might want to comment, oh, I didn't even check the 210. Oh, sod it. Anyway, I'm not going to go back to the 210 because we ain't got that kind of time, because it's just taking me ages to flick because I ain't got it in front of me. But the 210 will relate to something. All you got to do is go and look and see what it relates to, and that's going to pick you up. So you can get through, and you've already got 3 out of 6, and you haven't hit the NMR. Now I want to hit the NMR, so let's hit the NMR. And all we need to do is start on any one of these and just explain it. Now, first of all, I'm going to know the molecular formula. So we can learn the molecular formula from here. Anyone got an idea? Who can put up in the chat what the molecular formula is based on the integration value? So the integration value is the ratio of hydrogens We got 4 hydrogens, but my integration value is 1133. So that's telling me there are 8 hydrogens, which means I need to times that. My actual molecular formula is C4H8O2. So always check, if you've been given the empirical formula or the MR, always check this. This is the ratio of hydrogens to each other. So really, we're going with 8 hydrogens here. So the molecular formula is going to be C4H8O2. And that kind of makes sense because we said there was a carbonyl group and a hydroxy. So how could we have 2 oxygens if there was only 1 oxygen? So again, it makes sense that the molecular formula had to be doubled. So now we want to just comment on each one of these. If you comment on each one of these, you get 5 out of 6. If you explain what each one of these means, you get 5 out of 6. So just explain what each one of those means. If you can't put it together, who cares? So you're going to go chemical shift like 3.9. So we're going to go, this is purely for NMR now. We want to say the chemical shift at 3.9 ppm. You want to say what it is. So I'll do that in a second. I'm just going to put an equals. I want to say the splitting pattern is quartet. What does quartet tells you? It tells you the adjacent carbon. So the adjacent carbon has 3H, right? I can't fit everything in here the way I'm doing it. So quartet tells you the adjacent carbon has 3H attached. This is going to pick you up 5 out of 6 marks. If you have a quartet, the carbon next door has 3 hydrogens attached. The old N-1 rule, whatever it is. There we go. And now all I need to do is locate what that is. Oh, the integration value. So I'm just going to call it IV. You can't call it IV, right? But I'm going to call it the IV, the integration value of 1 means 1H in this environment. Okay, so the integration value means there's 1 hydrogen in that environment. So that carbon has 1 hydrogen like this. Get it? And it's attached like that. Now we need to find what does the 3.9 equal? This the long bit. So let me just zing to, what I need to do is copy and paste that thing and bring it back down here. Let me just copy and paste that. Hold on. I will copy. We will go down. We will paste it right here. And then what does 3.9 equal? Let's go to 3.9. 3.9 is telling me 3.9 is going to be this one. We know we've got an alcohol and that, so I don't think we can have the ester link. I don't think we got the ester link. Was it more than 3.9? I hope it weren't 3.91. It's 3.9, so that's probably telling me, oh, that is looking like an ester link, isn't it? What else? No, there's no halogen. So it's either that, I don't think we can have an ester. Yeah, anyway, I would say you got an H with an O, so it's probably OH, and then we've got, so that's probably the alcohol group. Where are we? We're over here. So we might want to say that this tells me that it has an O, right? So that's probably the alcohol attached there. So that's really what you're doing there. Then you want to just repeat for 3.7, singlet. No, there 3.7. So 3.7 is going to be a carbon attached on the other side maybe, and it's going to have 1 hydrogen in that environment. The carbon adjacent has no hydrogens attached. 2.1, what is 2.1? 2.1 is a singlet, so we just want to say the carbon next door has no hydrogens attached, but the actual environment has 3 hydrogens in it. And then over here, so it's a CH3, so that's a CH3 attached to a carbon with no hydrogens attached. And then we've got a doublet. So at 1.2 we have a doublet, and that is a carbon, a methyl group. So that's going to be a CH3, and that's a CH3. And these guys, this has a CH2 attached because it's a CH1 attached, sorry, because it's a doublet. And this CH3 has a carbon with no hydrogens attached. And here we go. I've run out of room, but yeah. So it should be all good. And then we're going to piece it. And then you're going to like piece it all together. Just listening to my kid. My kid's rowing next door. So let's have a go at piecing this together. All right. And then you're just going to piece this together. So why don't you have a go at piecing this together, guys? But what I'm trying to tell you is don't skip the H&MR. Spend 6 minutes on it. Just explain what each of those things means and you will pick up most of the marks. They're not expecting you to be able to piece it together. But if you had to piece it together, listen, we just said, write it out. Look, we just said it's C4H8O2. Everybody cool with the fact it's C4H8O2? You should be, because we got 8 hydrogens here. The integration trace tells you the number of hydrogens. Compare that to the empirical. You know it's double, so you double everything else. Now we know that. Let's just smash it together like that. Let's just put 4 carbons in, and then go right. Well, we've got a quartet with 1 hydrogen. So we've got something with 1 hydrogen that is attached to a CH3. So I don't know. We're going to go like that. Go like that. What can we do? Let's just smash some things on. Right. We know there was a carbonyl from this, so I'm just going to smash a carbonyl on. Does that make sense? That would be a CH3. Yes, have a look, folks. Singlet, check this. Why singlet? It's next to a carbon with no hydrogens attached, and it has 3 hydrogens in its environment. So 3 hydrogens in its environment. Next door, there are no hydrogens. Makes sense with our carbonyl. Then we come here and we go, okay, somebody is next to a doublet. Somebody's next to a doublet. So, I don't know. This bad boy looks like another CH3. Why do we know it's a CH3? Because we've got an integration trace of 3. My face is all over that. Let me just move my face. Oh my good gosh. Come on, you dipstickus. Maximus Iridius. Yeah, so how do I know this one? Well, CH3, it's a doublet. What does the doublet say? The doublet tells you that the carbon next door has 1 hydrogen attached. So there we go. We know that's right. And look, we just smashed the OH on there, and that's probably it. That's probably us done. Look, C4, 1, 2, 3, 4, 5, 6, 7, 8, bosh, bosh, bosh. And then 3.7 is a singlet, 1 hydrogen. Well, look, have a look here, folks. This is saying I've got 1 hydrogen attached. That's the hydrogen for the singlet. That's the hydrogen here with the 1. And he says, look, I'm producing a singlet because I'm next to this idiot over here who doesn't have any hydrogens attached, right? So that is probably the 3.7 we're getting over there. And there we go. That's going to be our structure. So yeah, you can get all your 6 marks from that. And then there we go. Yeah. Okay. Okay, so that should be fairly easy. Just talk your way through it. What do you guys want to do next? Which question? If you've got a particular question from an exam board, let me know. Hold on. People have been asking. More NMR. I've got hundreds of NMR. Lots of NMR, millions of NMR, but you know, we could spend all night doing NMR. What does someone want to go over? Recrystallization. Recrystallization practicals. All right, let me give you a, let's go through a couple of practicals then. Hold on, give me 1 sec. I will smash a practical up. Give me a secondo, people. Give me one of the seconds and I will put the practical up, okay? Bear with me and we will smash through a quick practical. He says quick, but look at this, look at this. Absolutely brutal. OMG. Alright, let's go through this first and then I'll put the rest up. Let's have a little look at this. Yep. Oh yeah, we'll have a look. We'll have a look. Okay, this question's about the preparation of hexane 2O. Hexane 2O does not mix with water and has a boiling point of 140. So we got highlights. You know, I just be active in the exam. Keep yourself active. Okay, it doesn't mix with water. Okay, thanks for that, old bean. Hexane 2O can be prepared from hex 1ene. So this is the old, we do it the other way round as well, but obviously you can make hexane 2O from hex 1ene. Hopefully you know the reaction conditions. What is it? Is it steam? Phosphoric acid catalyst? No. Yeah, I can't remember. There's two ways. Two ways. I get them mixed up, but there's two different ways. Anyway, we don't need that. Measure out 11 centimeter cubed of hexene 1. So we've got 11 centimeter cubed. They're going to ask me some carefully. 5 centimeter cubed concentrated phosphoric acid. After 5 minutes, add 10 centimeter cubed of distilled water to the mixture and transfer the boiling tube to separate funnel. Shake the mixture. Allow it to settle. Discard the aqueous layer. Add a fresh 10 centimeter sample of distilled water and repeat steps D to E. Transfer the remaining liquid to a beaker. Add 2 grams of anhydrous magnesium sulfate and allow it to stand for 5 minutes. Filter the mixture under reduced pressure. You need to be able to draw the diagram for that. Distill the filtrate and collect the distillate that boils in the range of 130 to 160. Okay, so now we're looking at this. It's important to wear eye protection and a lab coat when completing this experiment. Suggest with a reason one other appropriate safety precaution for this experiment. What would you say here, guys? Wear gloves to stop yeah, gloves, acid. Yeah. Give a reason for adding the distilled water in C and F. Why do we add distilled water? What is the water going to remove? Remember, look what they said here. The hexane 2O does not mix with water. So what are we getting rid of by adding the water? What are we to remove soluble impurities? Thank you, Emily. So we're going to remove soluble impurities. Well done. And of course you're going to get an aqueous layer and a non-polar layer, and you like your non-miscible layer, and then you can like filter off the aqueous layer. Give a reason for adding anhydrous magnesium sulfate. So hopefully you know that it is a drying agent. Yeah, so it's a drying agent. Okay, let me put the rest of the queue up for you people. Now, you need to know this. So how would you complete this diagram? So complete and label the diagram of the apparatus. You need to label it and complete the diagram. Luckily, they've put a little delivery tube to a vacuum pump. But what goes in the top here, and what would we label it with? What goes in the top? This is to filter under reduced pressure. And it says label it, but yeah. Make Buchner funnel, Buchner funnel, Buchner funnel, and filter. Yeah, so you want the Buchner funnel. You might say, what is a Buchner funnel? The Buchner funnel is the one that's like white porcelain, like that. So I've got my Buchner funnel. Oh my god, that's disgusting. And I like to do a dotted line for the filter paper, a dashed line, sorry. That's not a very good label, but I ain't got that kind of accuracy on here. So yeah, filter paper and Buchner funnel. Just remember this. This is called filtration under reduced pressure. You do this when you're making aspirin as well. When you're getting a solid precipitate and you want to dry it and wash everything off, and you know the aspirin one where you dissolve in the minimum amount of hot solvent like hot ethanol or whatever, and then you recrystallize, you cool, and then you're gonna use a Buchner funnel and to remove all of your soluble impurities. So the Buchner funnel, but that's with aspirin. You want the solid. Here we actually want to get rid of the solid impurities with the Buchner funnel, and we actually want the hexene. So yeah. And then, like, why do we collect the distillate? Well, it told us there it was 140 that comes off. You're going to be also asked, what is the most likely impurity with hexan 2-ol? What's the most likely impurity with hexan 2-ol? We already know that we have removed the hex 1-ene, haven't we? Because we got rid of that in the aqueous layer. We're going to have hexan 1-ol. That's right, 2727. You're going to get hexan 1-ol because you're going to get a bit of each. So you're going to have a little bit of hexan 1-ol in there. Right, let's have a look at another. Let's have a look at another one. Hold on, hold up, folks. Let me find another practical. I'm just having a scan. Scan. There is a maths question for that. I won't do you the maths question. It's an amount of substance with density and all of that business. CNMR, no, we did that. We don't want to look at that. How about benzene? Are you guys all good with your benzene stuff? Do you know how to do the nitration of benzene and your Friedel crafts? Are you guys all good with Friedel crafts and nitration of benzene? All right, very quickly, let me just go through benzene for you. I'll talk about it. Let me just quickly talk about benzene for those of you that want to know about benzene. I just saw a benzene question. That was why, basically. So for benzene, remember there are 3 pieces of evidence. So come on, guys, give me the 3 pieces of evidence for against Kekuli structure and for the structure of benzene. So 3 pieces of evidence for this. What are the 3 bits of evidence for this structure, the localized structure? This is the delocalized versus Kekule. Now, don't think like you are allowed to use Kekule's structure. I can't spell his name. I know he has like a thing somewhere. I don't know where the thing is. It might be on the U. Anyway, what are the 3 bits of evidence? Excellent, thank you, Filori. It doesn't decolorize bromine water. Enthalpy of hydrogenation is more exothermic, or is the enthalpy of hydrogenation is less exothermic. So if we take, is the best way to say it than expected. So if we look at cyclohexene, if you look at cyclohexene and you add hydrogen across it, you hydrogenate it, you get minus 120 kilojoules per mole. So if you had the Kekuli structure, we would expect it to be times 3 equals minus 360. When we hydrogenate benzene, we actually find that it is less exothermic. Now, what is less exothermic? We would call it less exothermic enthalpy of hydrogenation. All right, so it has a less exothermic enthalpy of hydrogenation. You need to say that is because the benzene ring stabilizes, so more stable, yeah, more thermodynamically stable, whatever. Benzene ring stabilizes it. So lovely. That's one bit of evidence. The other bit of evidence was this is going to undergo electrophilic addition. So this would do electrophilic addition, decolorize bromine water. This doesn't do electrophilic addition. This does electrophilic substitution. So that's your second bit of evidence. What's the bit of evidence with bond length? Anyone put up the bond length evidence? Good. Benzene has the same bond lengths, whereas these bond lengths, the double is like 140 and the single is 153. Benzene is somewhere in, I think actually it's 134. Benzene's is 140. So yeah, these doubles are 134. They're slightly shorter doubles. They're stronger, thicker, more condensed. The singles 153, 134. Benzene's, every bond is identical. Do you need to know the numbers? No. So there you go. What you want to say is the benzene bond length is in between the bond length of a single and a double bond. So again, that's your 3 bits of evidence. Lovely bubbly. Let's get rid of that. Right, there are your 3 bits of evidence against that. You could be asked a question on that. Let's rinse through the 2 reaction mechanisms you need to know. Quickly have a look at that. We'll look at Friedel-Crafts acylation first. So you'll get these in, you're definitely going to get some of this in the organic synthesis section. So what have you got going on? Well, you've got Friedel-Crafts. So this is when we want to acylate benzene. We want to add a carbonyl group attached to benzene, or we want to add an ethyl group or a carbonyl group or whatever we want to add. You could use any haloalkane, but you want to make a strong electrophile. So something like right that. What is my product going to be? And what do we call what is this called? This is to make a strong electrophile. What is this called? This is ethanoyl chloride. Those are known as acyl chlorides. Yeah, so what you're going to do here, you are going to form AlCl4 minus, and you are going to get CH3CO plus, obviously, and that's your, ethanoyl chloride. You've now made your strong electrophile, and now all we need to do is show that attacking the benzene ring. Don't forget, I'm just talking you through this. It's where do I put the plus there? I find that really messed up. I find it really hard to do where I'm going to put my plus. But I'm going to show my electrons. I'm going to touch the ring. No diddy. And then I'm going to draw the arrow curling and going towards the positive. And then in the intermediate, what I want to do is show this. Oh, Sugar Ray Leonard, we don't want to do that. What they mean here is it's got to be over 4 sides. So 1, 2, 3, 4. My U has covered 4 sides. I'm going to put a plus in the middle of the horseshoe. I'm then going to do this. Some people do a dotted line, whatever. That's going to be my hydrogen. I'm not going to bother with a dotted line. And then I want to attach to that carbon. So I've got my carbon with my O, because look, it's going to attack that carbocation there, and then we've got our CH3. So I know I don't need to display this, but I'm just showing you how that's going to attach. And then of course this is going to donate the electrons. What kind of arrow is that? What kind of rubbish arrow is that? Anyway, that's going to donate the electrons back to the ring, and there we go. Great. Now you may get a 5 marker, which has happened before and has come up before, where they want you to show the Friedel Crafts. This is known as Friedel Crafts reaction. Using aluminium chloride as the halogen carrier. We might have to show the reformation of the halogen carrier. So obviously you're going to have a hydrogen ion removed here, and that is going to react with AlCl 4 minus, and we're going to get what? HCl plus AlCl3. Coolio! Listen. One of the issues that you might get asked about for 1 or 2 marks with using acyl chlorides. What is one of the issues with acyl chlorides? One of the issues is they react more vigorously than carboxylic acid. So that's very good for industry. You get faster rates of reaction. What is the downside to acyl chlorides? Yes, the hydrochloric acid, the hydrogen chloride is corrosive. Thank you very much. Nice. Good. Well done. Right, now let's rub all of this business out and let's have a look at the nitration. Do we want to do nitration of benzene? I'll just finish off with I'll just finish doing that, and then we'll get off of this subject. And I'll give you an organic synthesis question. I'll give you an organic synthesis. I mean, you are doing the organic paper, right? You're going to have KC. You can have KC tomorrow as well, but hopefully you're all good with KC. Yeah, reactant, products over reactants business. Don't forget to use volume. Don't forget how to do the units. What we got? Let's Are you guys okay with the nitration of benzene? Exactly the same mechanism. You're just going to get your nitronium ion. Exactly the same. So I won't go through it if you're all right with it. Exactly the same. You do need to know how to reform and show the acid is a catalyst, and which of the acids, the nitric or the sulfuric acid, is the one acting as a catalyst. You do need to know that. That's just going to come out. You're going to get the exact same reaction and you're going to nitrate benzene, but you need to know how to form that. Is everyone cool with that? Explain how making a carboxylic acid from an acid anhydride is addition elimination. 2727. Okay, nitration of benzene is fine. All right, let me do that then. Oh my god, talk about R2727. What are you trying to ask about? Yeah, the problem is I can't go quickly. You know, it's A level chemistry, isn't it? It's dense. It's dibby dense. Dibby. So there ain't really much going quickly. Let me give you. I will bear that in mind. You might have to ask me that again. Let me just give you an organic synthesis question. What question paper is this? What do you want? An organic synthesis? Oh my god. Everyone's shouting at the questions and I can't keep up with what is going on. Let me do an acid. Oh, where's my little book? And then I'll find you one. Hold on. Where's my little book? You know what? I can make these will be a lot better next year, but this ain't very helpful for you. But because what I realized is I don't have a list of all the exam questions and where they are, but I do know where some are. So like I know, like, you know what I mean, sit here just scrolling through. What I realised, about half an hour before the live, I realised, oh, what I need is... So that's called improvement for people in the future who I do lives for, but not for you guys. I was like, oh, I know what I need is, I need to have every single topic and a list on my wall of where the questions are. Then I can just pop them out nice and quick. Unfortunately for you guys, I ain't gonna have that in time for you, okay? No, not time for you. So what we're gonna do, I'm gonna give you a little ooh, that's another practical one. Yeah, oh no, that's volume of gas, that's dead easy peasy pudding and pie. Alright, let me give you this one. See if you can do this one. Have a go at this, peeps. Whoa diddly whoa. was that? I will do that acid anhydride thing in a second, but let me just mechanism, addition elimination mechanism of acid anhydrides, but it's very specific, like if it's going to come up. But I need some water. 1 second while I grab water. Oh, sugar. Sorry. Yeah, maybe that is an amide. Oh God, I hope not. It doesn't look like an amide to me. Um, so prilocaine is hydrolyzed, Draw two structures of organic compounds formed under acidic conditions. So we want organic structures formed under acidic conditions. Well, no, I'm going to do the acid hydrolysis. So think about acid hydrolysis. With acid hydrolysis, hydrolysis is going to happen wherever you have like a carboxyl group or an amine group. You can potentially have hydrolysis. So let's have a little look at this again, because let me double check. Let me double check. That don't look like a ketone. That's not a ketone, is it? No, that's not a ketone. Hold on. We've definitely got an amine over here. Oh gosh! Oh my god! Look at what a dipstickus. I just told you that. This is what happens when I'm tired, right? I just told you we got the double bond O, and that is the amide link. And look what's staring me right in the fat face of bald-headed face of mine. An amide link right there. So you have to have a nitrogen attached to a carbon with a double, and it's staring straight at me. There we go. Sorry about that, folks. It's not a ketone. We got amine over here and that. So now we're going to hydrolyze it. Where can this possibly break? This can break where we have hydrolysis will happen at the ester link or an amide link. Do we have an ester link? Do we have an ester link to hydrolyze? No, we don't have an ester link to hydrolyze. Do we have an amide link? Yes. So let's hydrolyze that amide link. Now, hydrolysis cannot happen here with the amine. That cannot be hydrolyzed. Okay, the amine is not going to be hydrolyzed. You need to have an amide or ester link for the hydrolysis here. Okay, so what we're going to do, we're just going to split that, and we're going to say, okay, baby, let's split that like that. Let's add back in. So we're going to go. Now, if it was base hydrolysis, we wouldn't have this. But this is acid hydrolysis. So we're going to add, we're not just going to go back to the original amine. We're going to make a kind of nitronium ion. We're going to add an extra hydrogen. So it would have been like that originally. If we'd gone back to the original product, it would have been like that. But due to the fact that it's acid hydrolysis, we're adding an extra hydrogen, right? That's the acid bit, because we are adding the acid hydrolysis in acidic conditions means we've got hydrogen ions knocking about. And remember, this, when you want to talk about amines, this here can accept, because it has a lone pair, this can accept that hydrogen. These electrons are available. Now, is this the best base possible? Is this the best ever base? No. Phenylamine is not the best base. Phenylamine is not the best base because you need to know about this. The electrons here are withdrawn into the ring. It's nothing to do with this question, but I'm just waffling because you might get this in the exam. Whereas if you compare that with, say, methylamine or ethylamine, if I add a little CH2 there, remember these are electron donating, so the lone pair on the hydrogen, I've drawn that really badly, but the lone pair on the hydrogen will be more available, so that will be a stronger base. The electron ring partially delocalized. If they ask you why this is a crap base, the lone pair of electrons are partially delocalized into the pi ring, okay? So we need to use the word partial delocalization, and that's what happens to this lone pair. However, they're still acting as a base in acid conditions and picking up the hydrogen. So one of our things over here is going to be this. If we want to see what the other product is going to be, the other product is basically that. And we're just going to bring it back to a... we're going to bring it back to an carboxylic acid, right? So... oh God, I don't want to. Do I have to draw that out? Can I skip drawing that, please? Would that be okay? We just stick an OH there. And if you want, if you absolutely have to, you can go that amine there will gain an extra hydrogen. Whenever nitrogen has 4 bonds, you put a plus next to it. So you could do that. Is everyone all right with that? Okay. Yeah, just the carboxylic acid. You don't have to put the extra nitrogen on that for the marks, but you can do. They'll allow you with that. Right. Right. Someone asked me a question about something else. Let me see if I can find something else on amines and amides while we're here. While we're knocking around amines and amides, let's have a butchers. Oh, I know what I wanted to do. Let me make sure. Um, Yeah, I would expect you to get like a 5-6 marker on the. I would expect you to get an aspirin or something like 5-6 marks on a yield, an aspirin, and just an amount of substance which you should already be good at. It will either be the cyclohexanol or cyclohexene, or you might get the ethanoic acid with the aspirin business. So you might get recrystallization. What I want to do. Oh yeah, let's do that one. Let's do that. Let's do this. Let me quickly do this one. Hold on. I know this isn't everyone's. This isn't probably on top of your list. My good lord. While I'm here, while we're here, folks. A little bit of amines. This is still amines. Quite a few of you in the thing said amines, amines. Give us amines. So I'm giving you amines because that's what you said. Lord of mercy. Define the term electronegativity. No, thank you. The ability to withdraw a pair of electrons within a covalent bond, something along those lines. And what is the explanation? Explain the polarity, define the term electronegativity, and then explain CBr, the electronegativity in CBr. Br is more electronegative than carbon, so the carbon becomes delta positive. Yeah, so you got like delta positive, Br, delta negative. The pair of electrons in a covalent bond are withdrawn towards this species because it's a more electronegative. Now what we want to do is we want to outline the mechanism for the reaction of 2-bromopropane with an excess of ammonia. It's basically you've got to do 2 steps here. So 2-bromopropane. Oh, I'm going to draw that, display that, sod it. I've not let myself enough room. We've not left ourselves enough room. I'm going to put the hydrogens there and there, and then 2. Oh God, I can't even read. I've lost the ability to read, folks. Okay, so 2-bromopropane. Oh God, can't I do that? I should probably just do skeletal. Let's not do skeletal. Let's do it like this then. Okay, with excess ammonia. So what's going to go on here, folks? What do I need to draw? Yeah, you guys are all over it. Cationic surfactant. I can see you badman in there, but do you know what cat? Why is it a good cationic surfactant? Why? So why is it a good cationic surfactant? Okay, so they're attacking that. And then what happens to the bromine? My bromine is going to bust off. And then what about the next step? What do I want to do in the next step? The next bit? Good. It's a bit like a phospholipid in biology. Hydrophilic, what is it? Hydrophilic head and a non-polar tail. So that means that it can kind of dissolve polar things and mix with non-polar things, I guess. Right? And then what we're going to do in this next one. By the way, a lot of you guys will be more comfortable. You'll probably notice I'm a bit of a dipstick when it comes to this because I don't use skeletal formulas. I'm a bit of a loser. And look, I'll probably lose marks because you should really write that like that, but I just ain't got that kind of energy. I'm not feeling that. So you have to bear with. You might want to use skeletals for these rather than copy my stupid brain power situation. Okay, what's happening here? This is now we got our little nitronium ion here. Where's the second? Oh, thank you, Ace Med. The second NH3 comes along and has its way with one of these hydrogens. And then I don't know if we have to draw the final product, but the final product essentially is we are going to, this is going to go there and get rid of that positive charge over there. The electrons in that bond will go there, get rid of that positive charge. And essentially, if I was to draw what it would look like after, for those of you that are really interested, it would be, I know this is an absolutely appalling diagram, but there we go, what we're going to do. And then you've got your amine. But remember, that has a lone pair. So here is where we get extra substitutions. This can now act as ammonia. If we have, look, it says excess. Check that. Check that. That's the clue. If you have an excess of the haloalkane, it means if there isn't an excess, then this doesn't have anyone to react with and we stop there. But if there is an excess, this is going to keep acting as ammonia and substituting for until this bad boy is until it's completely surrounded. All of them have been knocked off and we are completely surrounded with our quaternary ammonium salt, basically. But the formula for this would be absolutely, oh yeah, cationic surfactant. The thing is, I'll tell you what I can't explain. I can't explain how bad I am at skeletals, but essentially, because you're going to be, they're all joining on there. So that means that I'm going to have like, OMG, oh God. What the hell was that? Two methyls, carbon. Yes, that'll do me. Ah! Two methyls, carbon. All right, I'll do the. Yeah, I'll do that. So what is this? Give a use of the. So you see there, that's a quaternary. I always say quaternary because I'm a spaz. Quaternary ammonium salt. Okay. So what you've essentially done is you've carried on substituting. That has attacked another bromoalkane, and then you've then got like 2R groups, and then you attack another one, get 3R groups, and you end up with 4R groups, and that becomes positive. So you're right, cationic surfactant. Now normally this would be a bit of a crap cationic surfactant, this one here, what you would really normally need, so just bear with me. What you would normally need is one of these. If you want to make a good one, you'd add a haloalkane with a really long carbon chain, so something like, I don't know, bromoheptane, something like that, so that you end up with like 1, 2, 3, 4, 5, 6, 7, something like that. And that is going to be, so say that came from bromoheptane, you threw a bit of bromoheptane in there, you might get a sidey like that, and then you've got your non-polar tail, and you've got your kind of, all right, you've got your water-liking head. So it's a little bit like a phospholipid with your hydrophilic head and your negative tail, a little bit like that. So what you're saying is you've got a water-loving head and a, water-hating, a hydrophilic head and a hydrophobic tail, basically, because you've got a large non-polar bit on the tail. And that means that it's like, you know, when you get oil on your hands, olive oil, and you try to wash it off, it's immiscible. Well, if washing up, fairy washing up liquid has a lot of cationic surfactants basically. What is the cheap Tesco washing up liquid? The difference, if you look on the back, you will see less cationic surfactants, and there's anionic surfactants in them as well, but there's less basically. The good quality washing up liquid, why'd you pay £1.50 for fairy washing up liquid and 65p in the co-op for their washing up liquid? They have less cationic surfactants. Anyway, enough of that whiffle waffle waffle. I need to get on and find you another question, because let's go. Right. Yeah. Oh Lord of mercy, what is this one? Maybe, yeah. Reflux exam question. Alright, hold on, hold on. Oh, fudge a lub, lub, lub. Woodily woo. No, I don't like that. Okay, hold on, hold on, hold on, hold on. Let me get another one of these up. Let me get another one of these up. I'm just having a search, folks. Give me... Bear with, bear with, bear with. Okay, someone wants bioesters. I don't fancy bioesters, but yeah, we'll have a look at bioesters in a sec. I keep saying in a sec. The problem is, what is that? You're cool with zwitterions? Bond angles. Could give you a bit of bond angles. No, we don't fancy that. Bioethanol. No, that's from AS, but still, it's that can come up. Oh, that's Kekuli structure. You can get a 2021. They had a Kekuli structure one. But yeah, let's not do that. Um, oh, do you know how to make nitrobenzene? Anyone know the three conditions for nitrobenzene? Who's got the three conditions? No, there's no electropotentials. Does anyone know the three conditions for nitrobenzene? Yeah, 2727. Boom. Tin hydrochloric acid. Yeah. No, hold on. I think you were right. Tin and hydrochloric acid. Don't get shook. I think you're right, aren't you? Nitrobenzene, tin and hydrochloric acid. No, I didn't mean. Yeah, you can. I think you can use hydrogen, and if you reduce nitrobenzene, yes, to phenyl into phenylamine. Yes, yes, yes. You guys are right. I think you can use either. You can use hydrogen and platinum, and I think you can use tin and hydrochloric acid as well. So, or is it for the formation of nitrobenzene? You can reduce nitrobenzene to phenylamine. You can with tin and hydrochloric acid. You can reduce it with hydrochloric acid and tin. Absolutely more. Absolutely. If you want to form nitrobenzene, you're going to use sulfuric acid and nitric acid, aren't you? Concentrated sulfuric acid and nitric acid and 55 degrees. If you want to make nitrobenzene, but I mean, if you want to if you want to reduce nitrobenzene, you're going to use tin and concentrated hydrochloric acid. What am I doing? What am I doing? Where am I? What are we doing? KC? No, no. You all good with the EZ isomerism? I'm not doing more spectra. I want to kick myself in the face. No, thank you. Let me just give you a little thing here. then, and then I'm just going to give you a quick synthesis while I'm having a flick. Have a go at this. There you go. Yeah. See. So you've got we've got cyclohexanol. Step one, we go to cyclohexene. So what do we need for step one to go from alcohol to alkene? Yes, it is elimination. It is elimination, Big Nissy. So what do we need to eliminate alcohol down to alkene? We need sulfuric acid, and it's concentrated sulfuric acid, isn't it? Elimination, and I think you're going to have to be specific. I think it's concentrated sulfuric acid. Can we use concentrated phosphoric acid? Um, but you're going to defo need concentrated for that, for the elimination. Of course, what's the difference when you can go back the other way by using sulfuric acid with the alkene, but you need different conditions? You're going to need different conditions on the way back. So you're going to need to say dehydration or elimination, and you're going to need concentrated sulfuric or phosphoric. You can say either one. All right, what about step two? What are the reagents? Yeah, you can use both, but it's got to be conc. You just got to know when to say conc. You just have to know. Dehydrating is quite like serious business, so I think it's got to be concentrated for that. The other way round, it doesn't have to be concentrated. If you're going from the alkene back, you don't have to be concentrated sulfuric acid, but we still use, remember, you do that thing where you form the like ethyl hydrogen sulfate when you like you go from ethene and you add sulfuric acid, and then you warm after that, and you make it into an alcohol, right? Step two, compound G. And then compound G is going to that. What do we reckon we're adding in step two? Bromine electrophilic addition. Lovely jubbly. Well done, guys. So you're going to get 2 bromine atoms there, and then we're just going to do that there. Right, step three. How do we go from a haloalkane into an alcohol? Sodium hydroxide, yeah, but we need to be with the like what can we say about the conditions? Remember, we want nucleophilic substitution, so it's got to be aqueous. Thank you, Abdul Rahman. We want aqueous sodium hydroxide. Well done. We don't want ethanolic. If we did ethanolic, we would get an elimination, and we'd end up reforming the alkene, so we don't want that. All right, cool. Right, let's have a look at something else. Give me 2 secs. Secondo. Well, you got this question right. Let's give you the second part to this question. It's like, you know, do body, rubbing up style. Got my head half off the page. Bring me back. I'm so tired. We've got a 5 marker there. You might want to have a little go at that. Just jot it down on paper. See if you can do it. So this one for ethanoyl chloride. Now, someone was asking about nucleophilic. What were they asking about? Nucleophilic addition elimination. Isn't that what this is? Is this addition elimination? What is this? Surely acyl chlorides do. Do they do nucleophilic addition elimination? Yeah, nucleophilic addition elimination. So this is going to be very similar nucleophilic addition elimination to what you'd have with an ethanoic anhydride if you get that question with the ethanoic anhydride. So it's going to be similar. All the mechanisms are the same for this. Oh, my back is spangling. So what do we want to do? I guess it doesn't really matter which OH, but it would make sense for it to be this OH. Oh my God, how am I going to show that attacking that? Am I going to show that attacking that? So that's delta positive. Jeez Louise. I'm not very good at these curly arrows. That's actually foulesca. So I'm going to have to do some big fat arrow, which is like, jeez Louise, am I going to show that attacking that delta positive? So that's going to come round here and attack here. By the way, in AQA, I don't think you don't have to show delta positive, so you don't get marks for that. But you're going to get marked for the curly arrow coming round now. Now we're going to end up with 5 arrows. We're going to end up with 5 bonds around the carbon. I'm sure you know what's going to happen to the oxygen. What's going to happen to the oxygen? And then so we complete this step by showing that the oxygen is going to have to temporarily go to a single bond like that. So we're going to do that, and I'll lose a mark because the head of my arrow looks like it's had a bit of trauma. So now what I want to do is I want to connect these up, and we're going to draw the intermediate. Oh dear. Oh my God. We're going to have to display this one. We're going to have to move that out of the way. Jeez. That's going to be connected to the carbon. I've got my Cl. I've got my COCl. Oh my gosh. Now we've got 3 there. That's going to have a plus on it because that's now oxonium ion. Oxygen only likes 2 bonds. What's going to happen here now, folks? How are we going to get this double bond back? Or whatever. What's going to go on here? This is looking a bit crazy. This is looking a bit butts. What I probably need to do is I probably need to display these guys as well. Bring it back. Bring it back. Let's put the O and the CL there. Let's see what we got to do. Have I got all the O's? Oh, I haven't got all the O's. What a twit. What a twit. Thank you. Thank you. Thank you. Thank you. Thank you. I'm missing my O. Jibbly Joe. Right, let's display all the O's. Thank you. And that one, I need to show that, don't I, with the minus. So that's gone thingy. Oh, that looks so ugly. So what we're going to do, how are we going to sort this out? Hopefully, have we got the O back? Have we got the O back, or have we flop shotted? Oh. All right, lone on O, back to the double on the trouble. Which CL breaks off? Is it this one that breaks off? It must be this one that breaks off, right? Because if that's going to form a double bond, that's going to have to break off. What's going to happen with this? What does this hydrogen do? What does this hydrogen do? Where does the hydrogen go, guys? Help me out here. Does the hydrogen leave as well? Is the hydrogen going to donate the bond electrons back to that O to stabilize that O and bugger off? Is that going to happen? I think that's going to happen. So your hydrogen's going to leave, and your Cl is going to leave. And with all acyl chlorides, don't we always get an elimination of HCl eventually? We always get that coming off, don't we? I mean, I think we're always going to kind of work towards that when we're dealing with acyl chlorides. Generally, I suppose we've got to keep in our head that the OCl is getting eliminated, the Cl is getting eliminated as well, because we're going to end up with HCl with acyl chlorides, basically. Yeah, cool. That is it. That is it. That is it. Oh my god, that was disgust a longo. That was hideous. Oh. Oh, AI for prediction. I don't think, did it work? I don't think it worked. Let me ask the AI for a prediction. All right, let me ask AI for a prediction. I don't know if it worked on the first one, if anything came up.
What's your strategy?
Don't need any.
What's your prediction?
Prediction?
Yes, prediction.
Pain.
I don't even know if it did, but yeah, let's see. I don't know if it worked. I didn't even check. I didn't check with anyone. Let me ask the AI mode. Okay, let's ask AI mode. So here we go. We're going to go into Google on AI and we're going to ask it based, oh my gosh, you've got to get very specific. You've got to treat your AI nicely, right? So you've got to say based, and anyway, you got to, it's no good for you guys anyway, but it'll help people out next year if it works. So based on historical data and past papers, which topic is likely to feature heavily in AQA? You can do this for OCR and whatnot. Chemistry paper 2 in 2026 on Tuesday. Bosh. I don't know if I've asked it specifically, basically. I don't know if I've asked it. Oh. The two highest yield topics are rate. I mean, that's just bloody obvious, isn't it? Did I say A level? You know what? Let me. Did I say A level? Because that just seems dumb. These idiots are. These idiots are all on in A level chemistry. To start giving me the AI. Yeah, AI. I don't trust AI. AI is not working it for me. Okay. Based on the analysis of historical AQA past papers from 2017 to 2025, rate equations and aromatic chemistry of benzene and NMR spectroscopy consistently yield the highest concentration of marks. Don't believe me, peoples. You've got to believe what AI is telling you. It's telling you that the three topics with the highest yield of marks in tomorrow's paper are rate equations, kinetics, aromatic chemistry, benzene, this is for AQA, and NMR spectroscopy. Okay. %12 of the entire paper's marks will be on orders of reaction and rate equations, apparently, and the rate determining step. Arrhenius equation, expected to feature. Guess what? Started this live. I went through two Arrhenius equation questions. Equilibrium constants Kp and Kc were largely absent from paper 1. It's highly anticipated they are coming up in paper 2. It's often linked to reversible preparation of esters. Core organics, so basically Kp and Kc, get yourself with it, linked to reverse preparation of esters. It was absent in paper 1, so they think that that is coming up. Aromatic chemistry, benzene features without fail. Every single year benzene is featured, focusing heavily on electrophilic substitution, specifically nitration and Friedel-Crafts. We went through Friedel-Crafts. And the structural evidence for benzene stability, we went through the 3 bits of evidence. Boom. Carboxylic acids and their derivatives. Generally carries about 3 marks. Expect nucleophilic addition elimination mechanisms. We just did one involving acyl chlorides. Boom, we just did that one. Or anhydrides to form esters or amides. Preparation of amines, a high probability topic, including the reduction of nitriles or nitrobenzene. You guys know how to reduce nitriles, right? So you just add hydrogen, nickel catalyst, and yeah, the reduction of benzene we've just said you can do with tin and hydrochloric acid. Well, nitrobenzene. Okay. Yeah. No, you're right about KP, but okay. Ones that have been absent in recent years, they say to keep an eye on peptide links and zwitterions. You all know what a zwitterion is, right? So a zwitterion has an isoelectric point. At the isoelectric point, it will the charges on the zwitterion will balance out, so it will have the same amount of minuses as pluses. This can be at a specific pH. The isoelectric point of each different amino acid can be at a different pH. So zwitterions may come up, peptide links, distillation, reflux, preparation of cyclohexene or ethanol, and purification using a separating funnel and drying agents. Yeah, you know, calcium chloride anhydrous or magnesium sulfate anhydrous are your drying agents. Okay, cool. Remember, all AI does is look at all the other all the chemistry tutors. It's just a search engine, so it just looks at all the chemistry tutors who've made pretty like good predictions or whatever, you know. So we got the nucleophilic addition elimination right here, even though this was a foul, disgusting one, basically. This was a grim one. All right, 1 second though. Let's have a little butcher's hook at this, and I just want to see. Yes, blip, blip, blip. We did right. Yeah. You guys probably need to go on and do your own revision because I am flaking. I'm starting to flake. I don't know when the last time zwitterions came up. I can try and find one. Complete figure 3 to show the structures of 2 reactant species with curly arrows and relevant lone pairs of electrons involved in the formation. So this is going to be nucleophilic addition again. Yes. So you just got to work out what the reactants are for this. So we're gonna have an acyl chloride. We can tell there was an acyl chloride knocking about here. And remember, this is like in the first step. So there must have been methanol attack there. Oh shit. Sorry. Yeah, well spotted, whoever spotted that. And you might be thinking, how the fudge do you work that out? Remember, we just did this. So remember, this was after the first step. This is an intermediate from the first step. So we must have had methanol, right? Methanol. We must have had that attacking that carbon on the acyl chloride, which must have been like this. Everyone get that? So we had this acyl chloride, which is what? Ethanoyl chloride. No, it's not. It's propanoyl chloride. Propan oil. Oh gosh, it's getting late. I'm gonna have to shoot in a second. So we've got propanoyl chloride, and then this is attacking that there. So you've got methanol. Oh, sugar. Jesus. Yeah. Yeah, nucleophilic addition elimination. All right, guys, listen. Good luck. I am going to leave you here because I you have there are better uses of your time. What I suggest is going on PMT, working through questions, looking on TikTok, watching videos, looking at short, sharp ones on topics that you want to go through. Um, and that type of thing. Remember, you can look up organic synthesis in the back of your revision guides and just study the organic synthesis. At this point, you are just before your exam. If don't try to learn really difficult stuff that you've never been able to grasp over 2 years, don't try and crack it now. Just try and say, right, if this question comes up, how am I going to maximize my marks, like get 4 out of 5 or 3 out of 4 on specific topics that say you always get baffed by. So like if you go to the back, if you've got the CGP, go to the back and study the synthesis, learn the reagents, learn where it's concentrated, sulfuric acid and that kind of stuff. You'll pick up tons of marks. All right. I haven't covered a lot today. I would have loved to cover the whole thing, but you know, there just ain't that kind of time. I did a 4-hour live yesterday, so I'm knackered and I'm moving too slowly. And really, you're going to be able to optimize your time a lot better. So, guys, take care, and I will be going live for paper 3. I think for paper 3, I might just do like paper 3, you're going to have like 35, 36 multiple choice questions. So the main thing for paper 3 is go through loads and loads of packs of multiple choice questions and become really good at that, because that's the main thing for paper 3. And then any practicals that don't come up tomorrow and didn't come up in paper 1, you might be what's going to come up in paper 3. So paper 3 is going to have like 3 or 4, maybe max 5 questions, probably 4 questions, and then 35 multiple choice. So sometimes it's only 3 questions, sometimes it's 4 questions, and there'll be a practical in there, and a big fat practical, and then a load of multiple choice. All right, guys, good luck, good luck, good luck. Smash the exams, guys. Just remember, you've worked really hard, so yeah, you can do this.
Stick around.
I'm gonna have to science the shit out of this.
Take care, take care, take care.
You're still here? It's over.